Yeah, hi everyone. Sorry about the delay. I had some issues with this external monitor, but I think we can get started now. So we started covering sets, and so today I'm going to cover some basic set problems. And then before that, actually in preparation for our next quiz, I'll still do a couple of kinds of proofs that you will see in the quiz just as an exercise because, you know, the quiz is coming up soon. Okay, before we see our practice problems, let me make a couple of announcements. We are right now grading homework 2. We should have the grades ready in maybe 2 or 3 days. There is a lot of students, so grading is taking up a lot of time. Then quiz 1 scores are out. Just as a quick reminder, you have 1 week to request regrading after we publish the grades. So I think we publish them Sunday night, so you have until Sunday to request regrading. And you can request regrading through Gradescope. So it's pretty easy to do it through Gradescope. Yeah, I want to post the breakup of the grades, but I didn't manage to print it out. And so, but I think it looks good. Quite a lot of people are somewhere in the 80 to 100 range, which is really good. Okay, then quiz 2 will be next week. So the same as quiz 1, it will be on Tuesday. And you will have again a 1-hour window between 7:30 a.m. and 4 p.m. The material that will be in quiz 2 are proofs. So all sorts of different proofs that we were doing in the past couple of weeks. So sets will not be in quiz 2. And also the material that was covered in quiz 1 will not be directly in quiz 2. I think I already noted this. I'll note it one more time. I think traditionally students find this quiz to be the hardest one. You know, proofs, you know, kind of sometimes it's hard to wrap your head around reduction and so on, which is definitely going to be on the quiz. And so, so make sure to study a lot for this quiz. If you're stuck, come to office hours and so on. And then, again, I will stress this out one more time. You know, apart from the power outages and so on, there was quite a few students had issues submitting quiz 1. And because it was a weird week, we were very lenient in terms of how we were accepting submissions and so on. Lots of students emailed their submissions and things like that. We are not going to do that for quiz 2. So we did add additional 15 minutes into your grace period. So you have 1 hour to work on the quiz, and then you have another half an hour to submit it. And that's really a lot of time to tackle any kinds of issues that you have submitting it. I mean, you can even, you know, if internet goes down, you can walk to your neighbor's house and submit there or something. So make sure to really know how to submit your quiz using Gradescope. Make sure to read the syllabus and announcements about the quiz. Make sure to read instructions for how to submit it. For example, lots of students did not tag their solutions in Gradescope. And again, in quiz 1, we were lenient about that. We didn't deduct any points if you did not do that. We just TAs went in and manually did it instead of you. In quiz 2, we will not be doing that. So if you forget to tag your solutions in quiz 2, you will lose 20% of your points. So really make sure to understand how to submit your quiz. Okay, so these are, one final announcement. So homework 3 is out. It's due on Friday, October 9th. So after the quiz, so you should have plenty of time to work on this homework. Okay, any questions about any of these announcements? I don't know which TA is covering questions. Okay, I guess I'll do them out.
Yeah, there is a.
Other than the textbook and the practice quiz, is there anywhere else we can get extra practice for doing proofs? Anywhere we can find more practice problems? So that's a good question. You can try searching online and see if you can find problems. And I guess if you really want more problems, you can message us on Piazza, and we'll find problems for you. So if you solved everything in the textbook and the practice quiz, and you want more problems to practice, either try to search on your own. You can find lots of induction proofs online and so on, or ask us on Piazza, and we'll find more problems. So another question, will there be set proofs in quiz 2? I didn't see any in the practice quiz 2. So no. So nothing about sets will be in quiz 2. Let me just double check exactly the chapter in the book. So chapter 2. So quiz 2 will cover the material that is in chapter 2. So nothing from chapter 3 will be in that quiz. That will be in quiz 3. Any other questions? Okay, so let's do a couple of problems. I think I have 3. So these are the kinds of problems that will be in quiz 2. So this is still material from section 2 that I want to practice because quiz 2 is coming up next week. Okay, so let's do one proof by contradiction. So we want to show using proof by contradiction that there are no two integers x and y such that 24x plus 12y is equal to 1. So that is a very simple proof by contradiction. So if you remember the proof by contradiction, you have to assume the opposite of your proposition. And then starting from there, you have to derive a contradiction. So our proposition is that there are no two integers x and y such that 24x plus 12y is equal to 1. So what is the opposite of that? The opposite of that is that there are two integers x and y such that this holds. So we have 24x plus 12y is equal to 1, such that x is an element of z and y is an element of z. Okay. So this is what we start with. And from here, we want to derive a contradiction. Somehow we maybe probably want to show that either x or y is not an integer. And how do we do this? This is actually a really simple one. It's simpler than what you would expect maybe. So starting from this, we can divide both sides by 12. And so we get 2x plus y is equal to 1 over 12. Okay, now we started with the fact that x and y are integers. And so from the closure of integers, it follows that 2 times x plus y is also an integer. And that follows from closure of addition and multiplication. So we know that 2 times x plus y is an integer. And we also know that 2 times x plus y should be equal to 1 over 12, which is a rational number. And so these two things contradict each other. So this is a contradiction. And hence, we proved the original statement. So that was a very easy proof by contradiction. It actually looks maybe more complicated once you kind of look at it, but it's pretty easy to do it. Okay, any questions? Let's see.
Yes. Aren't proof by...
Okay, great question for Erickson. Aren't proof by contradiction of the form P and not Q? Yeah, I actually wanted to do this one intentionally because it has this slightly different form. So if your proposition is of the form P implies Q, then you start your proof by contradiction by assuming P and not Q. So that is totally correct. However, in this case, your proposition is just P. And so in that case, your proof by contradiction starts by assuming not P, and from there you have to derive a contradiction. And so there is a connection between these two. So negation of P implies Q is actually equivalent to P and not Q. So proof by contradiction always follows this general structure that you assume the negation of your proposition. And so this is what we did here. A special case that we've seen a lot is that when our proposition is P implies Q, then its negation is P and not Q, which is what we assume. So I hope this answers the question. Any other questions? Okay, wonderful. Okay, let's do this proof by induction. So we want to prove using induction that for each integer n greater than or equal to 1, 5 divides n to the power of 5 minus n. And I gave you 2 hints here. So first one is how you write out x minus 1 to the power of 5, which will come handy once we start working the proof. And another hint, and often I will not give that as a hint, but I think in this case it makes the proof easier. So try to do this proof by doing your inductive hypothesis for n minus 1. So you assume that 5 divides this holds for n minus 1, and then you want to show that it holds for n. And I think it's a little bit different proof by induction than what we've seen before. But I'll give you a couple of minutes and try to solve it on your own. And then I'll do it. I'll do it for you guys. Let's also do breakout rooms as well for a couple of minutes, so you can at least discuss how to start with your colleagues.
Hey, Zvonimir? Nope.
Okay, welcome back, everyone. I hope at least some of you managed to prove it. So let's give this a try. So what do we want to show? We want to show that for all n greater than or equal to 1, n to the power of 5 minus n is equal to 5 times, let's say, q, where q is an element of z. So that follows from the division theorem, right? So this is what I want to show. So let's first do our base case. So that's when n is equal to 1. And so we have 1 to the power of 5 minus 1 has to be equal to 5 times q. So we have 0 has to be equal to 5 times q. And that's holds where q is equal to 0. So we showed our base case. Now, let's write down our inductive hypothesis. And as I hinted, I think the proof works a little bit easier if we do the hypothesis in terms of n minus 1. So what is our hypothesis? Blah, 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 blah. So the hypothesis is that n minus 1 to the power of 5 minus n minus 1 is equal to 5 times some p, where p is an element of z. Okay, so we assume that 5 divides n minus 1 to the power of 5 minus n minus 1. And we want to show in inductive step that n to the power of 5 minus n is equal to 5 times some r. So this is what we want to show. Okay, so let's let's use this hint that I gave you here to write out our inductive hypothesis. So what do we get? So in the inductive hypothesis, we get n to the power of 5 minus 5 n to the power of 4 plus 10 n to the power of 3 minus 10 n squared plus 5n minus 1. So this is from the hint. So I expanded n minus 1 to the power of 5. And then I have this leftover part. So I have minus n plus 1. And I know that that is equal to 5 times p. Okay, so this is the hypothesis. And we want to show that something holds about n to the power of 5 minus n. So we already actually have this here. So let's see what that is equal to. So we have n to the power of 5 minus n is equal to we move everything else to the right-hand side. So we have 5 times p plus 5n to the power of 4 minus 10n to the power of 3 plus 10 n squared. 1 and 1 cancel each other, minus 5n. And that is equal to 5 times p plus n power 4 minus 2n cubed plus 2n squared minus n. And that is equal to 5 times some r, where r is an element of z. And that's it. So we showed that n to the power of 5 minus n is equal to 5 times r. So we showed our inductive step, and that concludes our proof. So let me take a look at the questions. But one thing I wanted to say about this proof is, especially when you're working on when you'll be solving quiz 2, clearly a hint like this we're going to give you. We're not expecting for you to know this by heart. And there is kind of a structure to it. I mean, you have to figure out how to use the hypothesis and so on. Sometimes you just get stuck on that and maybe you'll run out of time. Having said that, definitely make sure, even if your solution is partial in the quiz, make sure to denote the structure of proof by induction. So write down your base case, write down your inductive hypothesis, write down your inductive step, and so on. We will definitely be giving partial credits, and especially if we see that you know the structure, you know what you're doing. Maybe you just got stuck on the inductive step and you couldn't really prove it completely. But if you know the structure, you'll get a good number of partial credits. So that's just an advice for the quiz. Okay, let me look at the questions. So there's a question from Sang. So if the hints are given in the quiz, are you free to use it without proving it? Yes, most definitely. So whenever we give you a hint, you can just plug it in without worrying where it comes from and proving it and so on. Okay. Okay. Let's move ahead. Sorry. Another question, how did I plug in n to the power of 5 minus 1? I'm not sure exactly what you're referring to. How did I use the hint in inductive step? So the hint is used when I'm expanding n minus 1 to the power of 5. So I expanded that into this big expression down there that I'm just putting in parentheses. And so that's where the hint is used. Okay, let's move on and do one last pigeonhole principle proof. So we want to use the pigeonhole principle to prove that given any 7 integers, there will be 4 for which the sum of the squares of those integers is divisible by 4. So I will start this proof for you, but in the interest of time, you'll complete it at home once we get to the direct proof part. So As a reminder, how does pigeonhole principle work? So if you have n times n plus 1 objects and you distribute them among n containers, then there must be some container containing at least n plus 1 objects. So from this, we can calculate how many containers we need in this problem. So we know that there will be at least 4 for which the sum of the squares is divisible by 4. So at least 4. So that means that n plus 1 in this problem is equal to 4. And from here, we know that m is equal to 3. And then we also know the total number of objects. We have 7 integers. So m times n plus 1 is equal to 7. And if we plug in m into this, we can calculate that n is equal to 2. So we need 2 containers. Okay, and now the tricky part, what should these containers be? To be able to prove this, so that the square of those integers is divisible by 4. So in one container, we are going to put integers that are even. And in another container, we are going to put integers that are odd. There is no good kind of cookbook for how to figure the strategy for how to place objects into boxes kind of automatically. So this requires some trial and error, and there are definitely patterns. If you solve a few pigeonhole principle problems, you'll kind of notice them. And so this is the strategy that we're going to use in this case. Okay, so now that we defined how we place integers in the containers, we still have to show that, if we have 4 integers in one of these boxes, the sum of squares is divisible by 4. And so there'll be 2 cases here. So either you have 4 or more in this box, or you have 4 or more in this box. So this is going to be case 1. And this is going to be case 2. And so now you still have to prove each of these cases. So you have to show that, there are 4 or more integers and that are even, then the sum of their squares is going to be divisible by 4. And you have to do a similar thing for case 2. And so that will be just direct proof. And it's actually pretty easy to do it. So in case 1, you will have something like, 2 and 1 plus 2 and 2 plus 2 and 1 squared plus 2 and 2 squared plus 2 and 3 squared, and so on. And you have to show that this is divisible by 4. And so when you, plus 2 and 4 squared, I'm running out of space here. So when you kind of square this, you're going to get 4 and 1 squared plus 4 and 4 squared. And you pull out 4, and in the end, you're going to get that is equal to 4 times some k. So this is going to be case 1. and case 2 is going to work out similarly. So I'm not going to do these cases here completely for you. I suggest you guys do it at home. This is just kind of a direct proof that uses division theorem and so on. So any questions about this this problem?
Will you eventually be posting the full proof?
Okay. Okay. So let's do a little bit of sets. So you know, in the lectures, a bunch of different definitions were introduced about sets. You have to know, you know, all of the set operations, set predicates, and so on. You have to know what their definitions are. You have to know how to use them, and that's important, and it's definitely something we'll be asking for in the sets quiz. And so, you know, there's the empty set, there's the universe. I'm not going to revisit all of these. The question I want to get to is this one. So I'll give you a couple of minutes to solve it. So, you know, there is a decent chance that a question like this is going to be in the quiz on sets. So suppose you have this set, set A, and this is its definition. And now for each of these statements, you have to indicate whether they are true or false. Well, by circling true or false or whatever. And so, you know, this kind of shows or exercises whether we really understand the definitions of all these operations and how to apply them to sets and so on. So why don't you guys solve it on your own, and then we can go through it together. And let's do breakout rooms again, and you can double check your answers with your peers. And some of them are kind of tricky and require some thinking. So let's do this. Okay, welcome back. So let me go through this. When I teach in person, this always generates all sorts of interesting discussions. I think it's an interesting question. So, is 2 an element of A? So sure it is. We have 2 right here. So that's true. Know the distinction between these 2 and this set that contains an element 2. So it's totally fine to have sets of sets, right? So A is an example of a set and some of its elements are sets. Then is the set 2, 3 a subset of A? So it means R is 2 in A, it is 3 in A, it is, and so this also holds. Is empty set an element of A? Nope. So that's false. Is a set that contains just empty set a subset of A? So here we have to check, to be able to determine this, we have to check, is an empty set an element of A? So it's not, and hence this is false as well. Is the size of A equal to 3? No, A has 1, 2, 3, 4, 5 elements. So this is also false. Is an empty set an element of a power set of A? So if you remember from the lectures, power set is a set of all subsets of A, and it always includes the empty set. So this is true. Then we have, is a set that contains set 2 an element and of a power set of A? So is this a subset of A? So is the set that just contains 2 a subset of A? It is. And so this is also true. Is the set that contains 2 and 3 an element of power set of A? Well, is set 2, 3 a subset of A? It is. And so this is true as well. And then is the set 2, 3 a subset of a power set of A? So that is false. That would mean that 2 has to be an element of a power set of A. And we know that's false right away because power set of A, all of its elements are sets. And just 2 is not a set. So is this pair an element of the product of A with itself? So that's false as well, because this set that contains just 3 is not an element of A. So this is false. So let me now take a look at the questions. Let me just go back a little bit. Okay, question from Max. Why is empty set not part of A when the first element of A is an empty set? Great question. So take a look at the set A. The first element of set A is not an empty set. The first element of set A is a set that contains an empty set. If let's write a set B that looks like this, let's say. So empty set an element of B holds because empty set is an element of B. In the case of A set containing an empty set is an element of A, not an empty set. So I hope this clarifies it. Oh, okay, oops, somebody already responded. Thank you, and sorry if I'm butchering your names. Thank you, Shul or Shal. I apologize. So yeah, so Erickson is asking if the question was, is set containing an empty set an element of A? That is true. That holds. Good question, Erickson. Derek is asking, why would the empty set of F be empty set? I don't quite understand this question. Sorry about that. And yes, so Sang wrote, then let's write another one. Is a subset of A. So is this true or not? So this is true. This is true because this guy is an element of A. So yeah, we'll have to wrap this up. Like I said, whenever I teach this in person, we create a lot of discussions, the same as now. But we're already over time, so we have to stop now. If you're still confused about this, please come to office hours, and then we can go in detail with every single one of these. So yeah, I'll stop here. Yeah, sorry about the brackets. Some of them look kind of nice, I think. And yeah, be careful about brackets when you're solving this. If it will be in the quiz, but not in quiz 2, but in quiz 3, the chances are it will be there. Okay, thank you all. So let's wrap this up.